going to look at logarithmic functions, or log functions for short. We're going to start off with the graphs of the log functions. I'm going to give away something about log and exponential functions, and that is that they are inverses of each other. So we're going to start off by looking at the inverse of exponential growth. So I have here the function 2 to the x that we graphed last time. I've got the x values and corresponding y values for this function. And now we're going to take that and graph the inverse of this function. Now, one thing that we learned when we talked about inverse functions is that we can reverse the domain and range for functions and their inverses. So that means that all of these x values we're going to put in for y values. So we're going to put y is -2, -1, 0, 1, and 2, and then those are going to correspond to x values that are the y values of the function. So I put in the 1/4 that corresponds with -2, 1/2 corresponds with -1, 1 corresponds to 0, 2 goes with 1, and 4 goes with 2. Okay, let's go ahead and graph based on those x and y values. So for x equals 1/4, we get a function value of -2. For x equal to 1/2, we get a function value of -1. For x equal to 1, we get y value of 0. For x equal to 2, we get y value of 1. For x value of 4, we get y value of 2. All right, so connect these points with a curve. We get this for the graph of the inverse function. For now, I'm going to leave the function input boxes blank because we need to give the definition of a log function before we do that, but we can fill out the characteristics. So the domain is going to be what the range was of the exponential function, and we can also see that there's no values of x that are equal to 0 or less than 0. So it goes from 0 to positive infinity, not including 0. The range is the same as the domain of the exponential, so all real numbers, -infinity to positive infinity. All right, we can also see that from the graph where there's no minimum value of y and no maximum value of y. All right, is the graph increasing or decreasing? All right, well, as we go left to right, it's always increasing. So it goes along with the fact that it is corresponding to growth. So it is increasing on the entire domain from 0 to infinity. X-intercept, this time we do have an x-intercept. It is 1, 0, and there is no y-intercept. Let's look at the end behavior to the right. As x values go to positive infinity, y values are going to infinity. As we go to the left, though, x values approach 0 and don't touch it or cross it, and y values are going to negative infinity. All right, this actually gives us a vertical asymptote. So our asymptote is not a horizontal like we had in exponential, it is vertical. And so it's approaching this vertical line, x equal to 0. Now let's look at the inverse of exponential decay. I have the function that we used for exponential decay, 1/2 to the x, and then the x and y values that we plotted. So again, we're going to just be able to swap the x and y values to come up with x and y values for the inverse function. So the y values that we will use are -2, -1, 0, 1, and 2. And then the x values, we'll take the y values from our exponential decay function and plug those in for x values. So x of 4 gives us a -2, x of 2 we get y value of -1, x of 1 we get y value of 0, x of 1/2 we get y value of 1, and x equal to 1/4 gives us a y value of 2. Now plotting those points, right, we get the point x equal to 4, y equal to -2, x equal to 2, y equal to -1, x equal to 1, y of 0, x equal to 1/2, y of 1, x equal to 1/4, y equals 2. Connecting with the smooth curve. All right, this time we're going to get also a vertical asymptote of 0. As x gets larger, the function goes to negative infinity. We'll fill in the name when we learn the notation for the inverse of the exponential decay. So let's fill in the characteristics. For domain, we've got 0 to positive infinity. The range is all real numbers, negative infinity to positive infinity. It is decreasing for all values in the domain, so from 0 to infinity. X-intercept, again, we've got 1, 0. Y-intercept, there is none. It does not cross the y-axis. End behavior to the right as x goes to positive infinity. All right, function values or y values are going to negative infinity because it's decreasing. End behavior to the left. Here, as x approaches this fixed value of 0, y values go this time to positive infinity. So that tells us that we have a vertical asymptote at x equal to 0. So we just looked at the graph of the inverse function for f of x equals 2 to the x, exponential growth with a base of 2. So now let's see if we can come up with the function for the inverse function. So we go through our steps. We're going to replace f of x with y. So that's just a notation change. We just take y equals 2 to the x. We switch x and y, so this becomes x equals 2 to the y. All right, here we want to solve for y. But we need to have a new operation or a new function to be able to get y out of the exponent of the exponent. So to be able to write down the inverse function, we need to define the log function. So if we let a be greater than 0 but not equal to 1, and if we have only positive values of x, then the logarithm of x with respect to base a is denoted by y equals log base a of x. So if we have that notation, this is what we say. Log base a of, and here's what that means. We say that y is equal to log base a of x if and only if x equals a to the y. So you can see how we can get this y out of the exponent and have it be equal to this log base a of x. All right, so this is where we left off trying to find the inverse function. We had y is trapped in the exponent. So using that definition, we are going to say that y is equal to log base of 2 of x. All right, so what was an exponent is now equal to a logarithm. This is a really key point and an important takeaway of this lecture. A log or a logarithm is an exponent. So it's a different term, but it is something that we're very familiar with. So a log or a logarithm is an exponent. The other thing to point out is our base of 2 here shows up as the base of 2 in the logarithm expression. All right, and I guess just to round it out, we've got the x. All right, that x here is the same as this x here. All right, the last step that we have in our finding the inverse function is to change that notation from y to f inverse of x. So we can say f inverse of x is log base 2 of x. Okay, let's go back and finish off the name of the inverse of exponential growth and inverse of exponential decay. So the inverse of exponential growth is y equals log base 2 of x, all right, what we just found. And then the inverse of exponential decay is y equals, the only thing that's different here is the base. Log base 1/2 of x. We can also generalize now and say that the function f of x equals a to the x and g of x equal to log base a of x are inverses of each other. All right, we're going to come back to this when we solve some equations, but just look at an example. Let's say that we have the function f of x equals 5 to the x. Well, the inverse function of that we can write down. We know that it is a log, and the base is 5, and it's of x. Okay, now we're going to practice going from the log form to the exponential form. So we're going from something that looks like this to something that looks like this. So this first form is what we call the log form. The second form is the exponential form because we have the y in the exponent. So let's look at this example. We have got log base 4 of 16 equals 2. All right, so we are not solving anything here. We're not evaluating. We are just rewriting. So we want to rewrite that in exponential form. So we want to rewrite it as x equals a to the y. Now we can identify what those three things are, which can be helpful. So a is the base. So the base is the 4. And x is what we are taking the log of, so that's the 16. And the y is what it's equal to, so that's the 2. Now we rewrite it as x equals a to the y, just making those replacements. So we're going to take and say 16 is equal to a, which is 4, to the y, which is 2. So that is that logarithm expressed in exponential form. And we know that that's true. 16 equals 4 squared. All right, here's another example. And by the way, this one and the previous one are like number 1 from the assignment. We want to convert this to the form x equals a to the y. So let's identify the different pieces of it. So x is equal to 8. A is the base, that's equal to 2. And y is 3. All right, so now we're rewriting this as x equals a to the y. Just make those replacements. We get 8 equals 2 to the 3. All right, which we know that that's true. All right, another example. We want to convert this to exponential form, so let's identify the pieces. X is what we're taking the log of, so that's 1/9. A is the base, that's the 3. And y is what it's equal to, -2. So rewriting it as x equals a to the y, we get 1/9 equals 3 to the -2. Now we want to go the other direction, and we want to start off with something that looks like this and convert it to log form. So we have 125 equals 5 to the 3rd. So let's just identify what the pieces are. So x is equal to 125, a is equal to the base of 5, and y is the exponent, which is 3. So now we want to write that as y equals log base a of x. So just making replacements, we get 3 equals log base 5 of 125. Okay, let's look at another example. This one and the previous one are like number 2 from the assignment. So we want to identify what the different pieces are. X is equal to 1/27. A is the base of +3, and y is the exponent of -3. So rewriting it in log form, we get -3 equals log base +3 of 127. In the previous section, we looked at the natural base e. Now we want to look at the log that goes along with this natural base. So if we've got log base of e of some value, well, we rewrite that as ln of that value. All right, so if we see ln, all right, or another way that could show up is in script writing, ln of some value, we want to immediately think, well, that is log with base e. So for example, all right, let's say we have ln of e. Okay, so just to remind us what that is, it's log base e of e. And let's say we want to evaluate what that is. It's something that we don't know. All right, well, let's just call it y. So if we rewrite this using exponential form, we are going to get e equals the base of e to the y. All right, if we have e equal to e to some exponent, well, we know that that exponent needs to be 1. So we get y equals 1. All right, let's try another one. Let's say we have natural log e to the 6th. All right, we want to evaluate that. Again, it's something that we don't know. We can just call it y. And then we can rewrite it using exponential form. Okay, we have this time have e to the 6th equals the base of e to y. All right, we have the same base of e on both sides. That means that the exponents need to be equal. So we get y equal to 6. Let's look at one more where we evaluate the natural log of e. And let's say this time it has the exponent a squared plus b squared. And we don't know what that equal to. All right, let's just call it y. Let's rewrite it in exponential form. Okay, we know that what it equals is e to the a squared plus b squared. Okay, that's equal to the base of e because it's a natural log with the exponent of y. Again, because we have the same base on both sides, we can say that y is equal to a squared plus b squared. Okay, we also have something called the common log, and this is the log with the base of 10. So if we've got log base 10, all right, of some value, we can write that as just log of that value. In other words, if you see a log without a base subscript, we assume the base is equal to 10. All right, let's look at this example, log of 1. Now, because there's no subscript base, we know that the base is 10, and we are going to use this to evaluate and figure out what that log of 1 is equal to. So we know that the result is 1, and that's equal to the base of 10 to the unknown exponent y. All right, well, anytime we have the result of a base to an exponent equaling 1, well then the exponent must equal 0. So we get y equals 0 because 10 to the 0 is equal to 1. Let's look at this one. Log of 1,000 equals some unknown exponent, y. So let's rewrite this in exponential form. So the result is 1,000, and that's equal to the base of 10, because it's common log, with an exponent of y. All right, so here we want to think of, well, what exponent on 10 is going to give us 1,000? Well, in this case, y is equal to 3 because 10 cubed is equal to 1,000. So our result was y equals 3. Let's look at this one. Log of 1 over 100 equals, right, some unknown exponent, y. So rewriting this in exponential form, we've got 1 over 100 equal to the base of 10 with this exponent of y. Well, we know that y is going to be negative, right? Because we take that 10 and then it's taking the reciprocal. Well, 100 is 10 squared, so y must be negative 2 because 10 to the negative 2 equals 1 over 10 squared, which is 1 over 100. We're going to evaluate some log functions using a calculator. If we have a common log or natural log, a scientific calculator has the functionality to evaluate those. So remember, what we're looking for here is 10, base of 10, this is the common log, so base of 10 to what exponent results in 200. So that what we're looking for is 200. So if we plug log 200 into the calculator, that results in 2.3010, and this continues on. It's an irrational number, so it doesn't terminate or repeat. We can round to, let's say, 3 decimal places. We get 2.301. All right, let's look at this one, natural log of 7. So again, we're going to be able to use our calculator, and let's just write down what it is that we're calculating. What we're calculating is the base of e, because it's natural log, to an unknown exponent. That's what we're looking for, and the result is 7. So if we plug in natural log 7 to the calculator, we are going to end up with 1.9459, and again, it's non-terminating and it's non-repeating. If we round that to 3 decimal places, we get 1.946. Okay, we want to evaluate log base 6 of 75. Now your calculator does not have log base 6 as a function, so here is where we want to use the change of base formula. All right, here's the change of base formula. So you notice that for any log base a of x, we can convert it using common logs or natural logs. So let's take our example. Our base is a equal to 6, and x is 75. All right, so let's go ahead and use the common log. All right, so what a change of base formula says is that we can take log base 6 of 75 and convert this into log, just common log of what x is. So x is 75 divided by common log of what a is, which is 6. We can plug both of those common logs into the calculator. Log 75 gives us approximately 1.875, and log of 6 gives us approximately 0.778, which results in 2.4096. Continuing, rounding to 3 decimal places, we're going to get 2.410. Now what if we had used natural log instead? So natural log of x, which is 75, over natural log of a, which is 6. Again, we can plug both of those into our calculator. Natural log 75, we get 4.317 non-terminating over natural log 6, which is 1.791. And we plug that quotient into the calculator, we end up with the same result, 2.4096, continuing approximately 2.410. All right, here's another example. We want to evaluate log 9 of 5. So what we're looking for is the exponent that we put on 9 to result in 5. We don't have log base 9 on the calculator, so we need to convert this. We can use either natural log or common log. Let's use natural log. So we're going to take natural log x, which is natural log 5, over the natural log of the base, which is 9. Natural log of 5, if we plug that into the calculator, we get 1.609 over natural log 9, which is 2.197. And doing that division, we end up with 0.7324, and rounding to 3 decimal places, we get 0.732. The last thing we want to do in this section is use the definition of a log to solve for x. That means we want to convert to exponential form. So let's take our base, which in this case is x, raise it to the exponent that's given, that's the 2, and that's equal to 81. So we ask ourselves, what squared equals 81? Well, 9 squared equals 81. So we solve that for x, we get x equals 9. Let's look at this example. The x shows up in a different place. We have log base 2 of x equals 4. Rewriting this in exponential form, let's take that base of 2, take the exponent, which is 4, and that's equal to x. All right, well, 2 to the 4, 2 times 2 times 2 times 2, that is going to be equal to 16. So we get x equal to 16.